So today we're going to talk about means and standard deviations and stuff like that. And over the next couple of weeks, you guys are going to have to run some statistics. Josie, it's okay. It'll be okay, I promise. Because when I'm going to ask you to do the statistics, I'll tell you like what statistic to do, and I'll give you even some help and some data and other things. I really like using a particular program called R. And R, those of you who have maybe been exposed to some ideas about correlation, R actually stands for correlation. So this program, it's completely free. You can download it off the internet. If you have a MacBook, it will work on that. If you have a PC, it'll work on that. If you're a Linux fan, yeah, Linux people, if there are any, it'll work on that too. So it's completely free and downloadable. All you have to do is go to Google and type in R, not A-R-E, just the letter R, and it should pop up and it will give you instructions. Well, the web page will tell you how to download it and install it. It's a very, it's a great program. I was trying to think of the right word. But a lot of people think that it's scary because it involves typing things as opposed to like point, click, analyze. You actually have to type some things. But it's really not that bad. And to make things even easier, there's another free tool that integrates really well with R, and it's called RStudio. And RStudio is pretty slick. So I have had IT install RStudio on this computer. They're also in the computers in the Psych Lab, they're the Psych Computer Lab in 124 and also in 140. So if you don't have like a computer at home that you can work on when you're doing your homework and stuff, you can use these programs at least in this room or those other two rooms that I just mentioned. So let's pull up RStudio. So if I give you a question on the quiz, it might say, what's the mean for this data set? And typically I'll put the data set into some fashion where you will just be able to copy the information, paste it into R, and you'll have your data set up and ready to go. And then all you'll need to do is type in the appropriate commands, which normally I will give you, at least in the initial stages. Wow, this gave me a lot of junk. They're installing packages. Let's hope that this works anyway. Yeah, okay. So these little like arrow signs, this is the prompt, and it's waiting for you to put in data. So just to give you a quick demonstration before we get into the class, I'm going to generate some random data from a normal distribution. So I'm going to call this data, and maybe I can lift this up a little bit. Rejoice. Yes. Yeah, data. And I'm going to say that data is basically a random, normally, I'm going to sample from a normal distribution, or a norm, and I'm going to take 100 samples. What you get when your keyboard not laid out the same as you want at home. I'm going to take 100 samples from a normal distribution, and then I'm going to enter the mean. Let's say the mean is going to be 50, and the standard deviation. Someone want to give me a standard deviation? 10. Okay, 10. Beautiful. So now I have my data, and I can just type in data, and boom, I can look and see all the data that it just generated for me. And this is really fantastic. You guys, I'm not going to ask you to do this in this class, but if you ever are in a stats class and someone tells you something and you're not sure how it works, like the central limit theorem or some other things, you can actually play around in R and generate data and see how things work for yourself. So today we're going to talk about means and standard deviation. So one thing I might ask you to do is to take a mean of something. And this is ridiculously easy. Mean, data, curse. So basically I took data. Did I type in data first? No. All right, so mean, and then in the parentheses, this means that I'm taking the function mean and I'm applying it to some stuff. And that stuff here is the data. I could have named this anything. I could have named this Dr. Knapp's awesome sample or whatever. So you can label things as you choose. You could use X and Y or buttercups and tulips if you guys wanted. Anyway, so mean, data, boom, 47.92. That was ridiculously easy. I want to take a standard deviation of my data. So there's this page up where I'm expecting the shift to be, and when you hit page up, it will go to your last commands, which makes it easy if you want to duplicate previous commands. Anyway, so SD, so standard deviation of data. Boom, there it goes, 9.06. Now we said that the standard deviation that we were going to use should equal what? 10, and the mean should equal what? 50. But we have 47.9 and also 9. Why? Why aren't they exactly the same? Pardon? No, it's not because of rounding. Actually, if there is a rounding error, it would be way down here somewhere. So, let's talk about the difference between a population and a sample. What's the difference between a population and a sample? Yeah, a sample is just a collection of individuals from that population, right? So when I set up here, I want this normal distribution. I want to take 100 samples randomly from that, and the mean of that population. So the mean of the population is 50. The mean, or the standard deviation of that population is 10. Does that make sense? But when we take a sample from a population, what can happen? It's going to change. Yeah, and in almost all situations, what we observe in the sample isn't going to be exactly what's true in the population. It will be close, but it won't necessarily be right on. And in fact, you'd almost never expect it to be right on just because of random variation when you're sampling. Who did you get this time? Who did you get the next time? Yes. Tyler? Yes!
If you already have the data from the population, why would you take a sample of that data?
That's a great question. If you already have the population available to you, why would you take a sample from that population? Anyone think of a good reason? It might be stupid.
No, I'm like playing for, like, to check for.
Oh darn, I was hoping that was going to be your answer.
No. I usually go well but to check for extraneous people within the population.
But if you have a whole population at your hands, can't you just see, oh yeah, this person's way, way out there?
I don't think this would work out there. So, well, I think the process.
If you plotted the data appropriately, which you can do with R, it should be really easy for some anomaly to rapidly show itself. So I quickly wanted to review the important parts of a graph because we didn't cover all of that. So we have a graph, we should have a title, we need labels for our dependent and our independent variables. We should have some scale indication. And the scale, it might not be something 0 to 100. It could be something like men and women. But that way, at least, we're going to be able to tell what those data are representing, right? Now, men and women doesn't work out for this example so well, so I'm going to change the scale. But the other things hold. So data, it's important to have the data in your figure, or else there's nothing to show. And if the data are relatively complex, you might want to have a legend too. Actually, let's go back to the males and females for something. Let's say that we're looking at, I don't know, test performance. We've got females and males. And this, the yellow here, this is the study condition. And our orange, this may be without study. No study. Something like that. When we have a legend, this is really useful if we have more than a single independent variable. right? Because maybe we're interested not only in how men and women perform maybe on tests, but we're interested in seeing if there's a difference between studying in men and women. So by including those data here, it's going to be confusing what that is unless we have a legend appropriately. But let's go back to Kat's example about seeing some crazy individual in some population. So maybe we're going to use a histogram, and we're going to see how many people are in each of these bins. So this is all pretty normal distribution looking, and then way out here we've got somebody like that, like Bill Gates when it comes to income. So even though if you're like looking at all the people, which you wouldn't be able to do just at once, by using something like this, a picture can be worth 1,000 words or 1,000,000 views, because you can see sort of the whole shape of the data. It summarizes the data for us. So if you had access to the data from the entire population, I would argue that you don't need a sample from the population to observe someone that's extreme in one area or some other area. If those data are there, you can just use R to plot it. In fact, let's do that. Let's plot the data that I created earlier. I can see it already. So I'm going to type in HIST, H-I-S-T, for HIST. HIST data. HIST stands for histogram. Enter, and boom, I have a nice little histogram. So it doesn't seem like anyone's way off there on any side, which we probably wouldn't expect given the parameters that we fed the data. I'm not going to talk about the normal distribution at length, but if you know about it, you wouldn't expect to find someone way out here or way down here very often. Okay, so that brings us back to the question. Why would you ever sample from a population if you had all the information about the population there? I would say, what I thought Kat was saying, is that that's stupid. It is stupid. I mean, if you have all of the data there, why only take a subset of that data? Maybe if you want to design some predictive software to like figure out who's going to be successful in college, and you have everyone's data about the current college students and their SAT scores and everything, what you could do is maybe take half of those data points and build your model off of those data points, and then try to fit it to the other half.
Yeah.
Because if your model is accurate of reality, then it should fit that other half pretty well, right? But then even there, you're not really interested in how well it fits the other half. Your real interest is in how it will fit the future people coming up.
Yeah.
Does that make sense?
Yeah.
So lots of times, we are very interested in the population because we want to say things about people. We don't want to say things about, well, my students or the 5 people that were in my experiment. We want to draw conclusions and inferences about people in general. So in general, the deeper people study material, the better they remember that. Right? That's a general statement, not based on the entire population. We haven't looked at the entire population. It would be nuts to look at the entire population. How big is the U.S. population? 250, 300 mil? Or is that underestimating things? It's been a while since I looked at the census data. Anyway, that's a ton of data. How are you going to get all that? Think of all the postcards you'd have to send out. And how many people wouldn't bother returning those things? You'd have problems with response rates. So for a lot of practical purposes, within psychology and other behavioral sciences, you will never, ever, ever have access to the population. So because you never have access to the population, what do you need to do? You're going to sample from that population and then try to base some inferences off of your sample onto the population. And we're going to talk about that a little bit today. So I showed you how to do some very simple things in R. Oh, one other thing maybe that I could show you quickly. So the mean that we took was 47.9, and it should have been 50, right? If the mean was perfect at identifying the true mean in the population. So how could I get a better estimate of the true population mean? Make the sample size bigger. Let's do that. So instead of having data as 100 samples, I'm just going up, and I'm going to make this 10,000 samples. So there's our data. And there's some fancy summary statistics that R can tell you. You can use something like summary. And this will give you the mean and a bunch of other things too. So the minimum is 111. The maximum is 93. The mean, 49.94. So that's much closer to the true population mean, which we set in this instance to be 50. So this idea about taking a larger sample size, this is really important. Why is it important? Imagine that we want to look at a relationship, right? Because I said that psychology is all about relationships. Relationships between amygdala function and aggression. So what are we actually looking for in terms of aggression? Well, maybe we could look at the mean number of times that the murderers chose to kill that guy before he turned into a zombie versus the mean number of times that the people who aren't murderers were going to do the same thing, right? Now the mean, there's something cool about it. It's an unbiased estimator. Does anyone know what unbiased means here? Yeah.
Completely as close to factual as it possibly
Sort of. It's close. Say what? Yeah, I think that's better. So the mean, if you take the mean, it shouldn't be skewed, meaning like off in one direction, more often than it's off in another direction. So if you imagine we have some population of heights, so we're going to take this classroom and we're going to sample all of you guys, so it would just be a population raw. We will come up with some mean. Can everyone stand up for a second? I want to get an idea for who's tall and who's not. Okay. All right, you guys can sit down. So imagine that I picked out 2 people at random. Now, I am not doing this at random right now. I'm pretending like it just happened. So I happen to go with Derek and Maya. Yes. So I go with Derek and Maya. And let's say that the average or the mean height for this classroom is 5'10". And if I take Derek and Maya, is my estimate going to be over or under the truth? It'll be over, right? Because you are 2 of the taller people in this classroom. What if, on the other hand, I had picked Natasha and Tori? It should be under, right? Now, the probability of me picking Derek and Maya is going to be the same as the probability of picking Natasha and Tori, right? So, some of the means that I take are going to be above the true mean. Some of the means that I take are going to be below the true mean. Very few of those means that I take will be way far above the true mean, right? Because if you think about how the population is distributed, so the height that I'm drawing here in the line indicates, it's sort of like a histogram, how many people are at different heights. So if I've got 20 people here in the middle, and only a couple people here on the ends, I'm going to be much more likely, even if I get Derek, to then pick the next person, it'll be someone in the middle. Does that make sense? So the mean is an unbiased, or a sample mean, is an unbiased estimate of the population mean because the means on average, not any one mean that we're going to take, any one mean we would expect to be above or below by some amount. But on average, if we took means over and over and over again, the mean of all those means should be right in the middle. Because some of the times we get 2 of the tallest people, some of the times we get 2 of the shortest people. A lot of the times we get people right near in the middle. Sometimes we get tall and short, right? So all of that should wash out. Not in any one sample. But theoretically, if we continue to do this for the rest of our lives, we took an infinite number of samples. So, let's get rid of R. Okay, so how do we get a mean? Does anyone know the formula? Let's say we have 3 points. 1, 2, 3. I like using simple data like this in classroom examples because it's really easy to use. What's the mean?
Yeah, 2.
The mean is 2. How the heck did you guys figure that out if you couldn't tell me what the formula was?
Add them together and divide by 3.
You add them together and then divide by the total number of observations that you have. Now, so the people who aren't big fans of math, they might get freaked out when they see something like this. Or even more freaked out if they see something like this. I equals 1, 3, I. There we go. Stop it. Stop it. The trick with a lot of the formulas is trying to explain them in everyday plain old English. Because if you can figure it out what it means in plain old English, it's really not that scary. So this thing here, does anyone know what Greek letter that is?
Sigma.
Sigma, that's right, it's sigma. So sigma, when we see it, it means we're going to sum up stuff. So what stuff are we going to sum up? We're going to sum up xi's. So here, if we have a set, these are all values that x took in our sample. We don't have to say x, we could say something like height. Height I, or IQ I, or whatever the variable that we're measuring I. So x is just a placeholder for that variable, and when you're writing big, long formulas, it's often easier just to say x instead of height, age, whatever. So we're going to sum up all of the values of the x. And this I means, if you imagine that, oh, this is probably bad. Let me reorder this. 2, 3, 1. So these are our data. What is the first x that we observed? 2. I here is 1. And the xi is 2. What's the second x that we observed? 3. So all this I means is basically just a counter that goes through the data. And we can tell you which data that we want you to go through. So we want you to start with I equals 1. So start here and go all the way up through the third x. If we had more of that, like say 25 or whatever. I often in class will not put those up there because it's a bit scarier. And once you sort of understand the basic mechanics, it's sort of implied what's going on, unless you want to only go through a certain number of them. So I'm just going to represent this as sigma x over n. So I'm going to sum up the x's and divide by n. So n is equal to the number of observations of x. So all this is really is just 2 plus 3 plus 1 divided by 3, which is equal to 6 over 3, which is equal to 2. Now, if you have a small data set like this, writing it out like this in longhand isn't that big of a deal. But if you have 100 observations, this type of notation allows us to communicate something much more succinctly. All we're doing is just adding stuff up. It's not hard. Just add it, add all of the x's, and divide by n. That's our mean. This particular form of the mean, if we have the entire population, we're going to represent that with the Greek letter mu. Mu for mean. So if you see mu, you know that we're talking about a population mean. If we're not talking about the population, and instead we're talking about a sample from a population, how would you guys represent the mean? Does anyone have what? A big M. Ooh, that's one way of doing it. I don't like using the big M because that looks too much like my mu.
I thought you had a longer tail.
My writing, excuse me.
Isn't it like an X with a bar over it?
X with a bar, X with a hat. Yeah. So that X bar, it means the mean of X. It's just a symbol. We could write it out longhand, the mean of X. But this allows us to be much more concise in what we're writing. So, mu is the mean of the population. X bar is going to be the sample mean. What if I had a couple different variables and I had an X and a Y? So this is a sample mean for what? Or X, right? So if I want a sample mean for Y? Yeah.
Same thing with just the thing over Y.
Yeah, I'd be summing up all the Y's and I'd use Y with a bar over it instead of X. Or if I wanted to write things out longhand, I could do
Oh,
age bar, which would indicate what? The mean age, yeah. Lots of times if we're working with multiple variables, there won't just be a mu, but there'll be another thing down there. Mu x, indicate the population mean of that x variable, whatever that x variable happens to be. Does that make sense? Is that scary? Yep. What's scary about it? What part do you need help with? Or is it just you need some practice? All right. For this class, I really don't want you adding up things like this, because that's not the point of this class. You have R. Just say mean. All right. So the mean, as I said, the sample mean is an unbiased estimate of the population, which is fantastic. So we've covered the mean. Let's move on to standard deviation. Or variance. What would you guys prefer to hit first? Maybe we'll do variance. What is variance? Does anyone know yet?
Is it like the range of the data?
It's something very similar to the range. So the mean tells us about the central tendency of the data. Like, if you think about things in physics, the mean literally is like the balance point for the data. So if we had some distribution, I'm collapsing over a histogram here, the mean would be right in there, right? If this was made out of metal, I could put it on my finger and it would balance. If, however, we had one bozo over here, where does the mean go? It goes over here, right? So the mean got shifted a little bit. No problem. So range, what does range tell us?
From how far to how far?
Yeah, range tells us how far to how far, right? All we need to do to get the range is to take the highest, subtract the lowest, and we get the range. Maybe there's a range of 30, maybe it's 30,000, maybe it's 30 million. We need some scale to figure that out. So the range is telling us how spread out things are. There are other things that tell us how spread out things are, like standard deviation and variance. Both the, oh, did I caught it?
Yeah, we were worried.
So both the standard deviation and variance tell you about how spread out data are. So if you think about it, there could be some situations where data aren't really spread out very much. And there could be other situations where data are spread out all around the place. Let's talk about robbing the cradle. So I am, let's say 38. I'm not positive. It's either 38 or 39. You can do the math, but I'm not interested in that right now. Anyway, so I am 38. My wife, she's 37. Creepy?
No. Yes.
How about if she was 27?
Wait, you
Still
gotta do the
fine?
math.
Could be worse. 17?
Yeah.
definitely
Yes.
illegal.
I guess it depends on the state, but yeah.
I know there's in Washington.
Shit, at least has to be 26.
At least 26?
Yeah, you're supposed to take your age, divide it in half, add 10 years, and that's your limit.
Take your age, divide it in half, add 10 years, and that's your limit. So, I'm 2. I take my age, divide it in half, I'm 1, plus 10 is 11. So I'm 2 years old, I should be dating an 11-year-old. Creepy?
No.
You're sick.
I guess you're right, it does kind of work that way.
Creepy, right? 2, 11? Well, let's make it...
Fine,
no.
if you're over the age of 18.
Okay. We can add in the... Basically what we're doing is we're taking a model, right? We have a model of the world, maybe taken from Glamour or Cosmo someplace, I don't know. And it seems to fit the data pretty well. But then we come out to these weird situations. Well, when you're 2, you should be dating someone who's 11, but they're 11, so they should be dating someone that's like 16, right? What the? Anyway, so that model that we have, our idea about the way that the world works when it comes to romantic relationships, it fails. So then we add in other parameters. We say, well, after a certain age or some other things, maybe we're not going to be, so ageist. Instead, we're going to focus on mental age. Because that little girl in Dune, I watched this last night with my son. She's like, she has the mind of a very wise woman, but she has a body of a 4-year-old. That would get a little weird too. But anyway, the point is, you take someone who's like 37 and you take 10 years off, or you add 10 years, and that's not that big of a deal. But you take someone who's 10 and you add 10 years or subtract 10 years. Whoa, why is that? Well, it's because there's a huge variability in the differences between a 10-year-old and a 1-year-old or a 21-year-old, and not such huge differences between a 30-year-old and a 20-year-old or a 40-year-old, right? So variability is a good thing to describe. As I talked about a couple classes ago, variability is crucial for us to understand what's going on. Because if we have no variability, if the thing that we're looking at is a constant, we can't learn anything from that. Are men more intelligent than women? I'm going to measure your blood to see if you have DNA. And that's my measure for intelligence. You have DNA, intelligent. Well, there's not going to be variability. You all are going to have the DNA, right? So I can't use that. That's a bad thing to use for intelligence anyway. So let me introduce another type of validity. It's called face validity. Anyone think of what face validity might mean? So validity is something that is doing what it's supposed to do. If something is valid on its face, what does that suggest?
Seems valid when you first look at it.
It seems valid when you first look at it. So if I'm going to measure your IQ by looking to see if you have DNA, does that seem valid? No, it's got like no face validity. If I want to test your IQ by giving you some tangrams and seeing if you can put them together to form a camel. You guys know what tangrams are? They're those little shapes, triangles and squares, and you put them together in different ways. They're fun. Anyway, maybe I look and see how long it takes you to put those things in order. Would that be a better way of testing IQ? Yeah, a heck of a lot better. And there'd be some better ones than that too. Okay, so what was the point that I was trying to make? All right, there's variability. Sometimes we have a lot of it, and sometimes we have a little bit of it. And using variance and standard deviations, we can describe the variability that's out there. So, does anyone know what the formula for variance is? Say we have the whole population. Variance. Yes, I think it's an A. Thank you. So how do we figure out how far people are away from the mean on average? Right? Because variability, like we can think about variations around the mean. So we could imagine two different distributions of people I drew a little screwy, but imagine that the mean is the same for both of them. This one is much more spread out around the mean, right, than is this. How could we figure out how far things are on average, how far they're spread out on average? Sorry. Take the mean. So I'm going to put a mean up here. Actually, we're doing population right now. Sorry, excuse me. Mean.
Figure out how far each of the data from the mean.
How far each of the data are from the mean. So let's just say we have one piece of data. How can we figure out how far that one piece of data is from the mean? So the mean for this class in height, let's say it's 5'10", I am 6'2".
6 is 2, subtract 5 from 10.
So you're saying we should take the observation, each observation, right? And put the I there and erase it so we don't scare people. So we're going to take each observation and subtract the mean from it, right? So there's like 4 inches of deviation. I am 4 inches deviant. Is anyone in here 5'10"? You're not at all deviant. Bless you. When we're talking about deviance and stats, we're not talking about moral deviance. It's not like I'm some bad SOB, you know, I'm deviant in that way. No, it just has to do with where you are in terms of the mean. So I am 4 inches above the mean. Who's 4 inches below? Anyone here 5'6"? Is that you, Josie?
No, not 5'6".
No, 5'6"? Anyone 5'7"? 5'7". Oh, wait a minute. My estimate of height was way, oh, right. You guys are standing up, right? This is tiered?
No.
This is the same on your level?
No. It's tiered, but we just want to be tall.
Okay. So obviously my mean estimate was really off. If one of the taller people in our classroom was only 5'7", forgive me, it's just an example, I'm making stuff up. Making up data, I'm not making up concepts. Okay, but, so if our mean really was 5'10", and she was 5'7", she is deviant 3, right? She's 3 below the mean. So if we want to get a sense for, on average, how deviant are people, how on average, all we need to do is do this, right? We have the entire population. We have the mean, because we were able to figure that out, and then subtract the mean from each person's score. And this will tell us how deviant we are on average. One thing I've left out are the parentheses. This is to indicate that you are taking the sum of this entire thing here. You're not just taking the sum of x and then subtracting the mean from the sum, or else you'll find a very different answer. Does that make sense? So all we're getting here, this is a deviation score. So if we summed up all the deviations and divided by n, what would we get? This is true no matter what data set that you have. It's not 1. Did you say 1?
I yawned.
Oh, you yawned. Your yawn sounded like one. Yeah. Has anyone figured it out intuitively? 0, you say. Yes, you are right.
I love my yawns.
How did you know it was 0? Or was that just a lucky guess?
Well, because if you're taking the deviation and then dividing it by the number of times that you find deviation, it comes down to 0. It's kind of like, I don't know, like a formula for it.
Your intuition is right on. So imagine we have this distribution, whatever it looks like. It doesn't have to look nice and smooth like that. It can be big and little, and then, yes, oh, no. Stay. So we have some distribution, and this is the balance point. This means that everything on this side exactly balances with everything on this side, right? Which means that if you add up all this stuff over here and add up all this stuff over here, it'll cancel each other out. Actually, I shouldn't say add up all the stuff, but add up all the deviations and add up all the deviations. It will cancel each other out. This might be, 223, and then this will necessarily be negative 223. So, this creates a bit of a problem, because if we just take the deviations by themselves, they will cancel one another out. So what can we do? We can square it. If we square it, they won't cancel each other out. You guys heard positive times a positive equals a? Yeah, positive. And negative times a negative equals a positive. So if you take anything, whether the deviation is positive or negative, if you square it, it will be positive, which will mean that this actually will be something that is non-zero. So this is the formula for the population variance. If we want to get the population standard deviation, I'm going to write right here, pop. I'm going to do STD. Population's STD, standard deviation. What's that? If you notice, the population variance, this is a sigma, that's the Greek letter sigma. So sigma squared is the variance, but just sigma is the standard deviation. So if this is the variance, how do I get standard? Yes, that's exactly right. Just take the square root of that. And in R, it's really easy to do. SD is standard deviation. VAR, VAR, is a variance. You can even do SQRT, which means square root of VAR, and verify that that is the standard deviation. So this is it. That's the standard deviation. Notice that both of these things are just means. Here we have a mean just of the data itself, and here we have a mean, well, the square root of the mean of the squared deviations. I want to emphasize this because a lot of people get scared about statistics, and they fail to recognize the patterns that are repeated over and over and over again. And if you can pick up on these patterns, stats becomes much less scary. So, that's the population variance. If we got rid of the square root, we square root it, we have the population standard deviation. But if we have the population, we don't need to take a sample, and we most often don't. So we need to get a sample variance and a sample standard deviation. So sample, we use S. S squared is going to equal the sample variance. And S is going to equal the sample standard deviation. And one very important thing to know is that unlike the sample mean, which is an unbiased estimate of the population mean, the sample standard deviation and the sample variance are not unbiased estimates of the population variance if you were to keep it in that type of a form. So we're not. So it's a biased estimate, which means that either it's typically overestimating the true variance or standard deviation, or typically underestimating the true variance or standard deviation. So what do you think it is? If we took a sample from this classroom and took the variance of that sample using the same formula that we used up there, would that variance on average tend to overestimate the variance or underestimate it? Underestimate it. That's right. Ding, 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 ding. Why? Just a lucky guess? More than a lucky guess. Intuition. That thing which helps us find the truth sometimes. Our intuition is right. Think about it. Although the means on average should balance one another out, most of the time that I take a sample, I should get individuals that are close to the mean, right? Because there are only a couple people way out there. And yes, some of my samples will have these individuals, but on average, they won't. Most of my samples on average are going to be of people in the middle. Does that make sense? So if I'm getting more of the samples of the people that are closer to the middle than the samples of the people way out at the edges, what's that going to do to my estimate of how spread out things are? It's going to decrease it. So we are going to change this formula ever so slightly. N minus 1. The formula for the means, it's the same either way. The formula for the variance and standard deviation, if you see n, we're talking about an entire population that we have access to. If we have n minus 1, let me relabel this. I'm going to say sample unbiased estimate of population variance. Pop var. Same thing, except pop standard deviation. So it's not that scary. This, we're just going to sum up things. We can all do squares, right? 2 times 2 is 4. 4 times 4 is 16 times 16 is 256, is that right? I don't know. Anyway, that's pretty simple calculations. All we're doing here is simple addition. Well, actually, first we're doing subtraction, then we're squaring that, then we're adding up all those squared values, and then we're dividing. So all of that's very simple, nothing too technical here. And what we get is an unbiased estimate of the true population mean. Again, this doesn't mean that our estimate is the population mean, but it means it's unbiased. That if we did it over and over and over again, we would expect the mean of those means to converge. Same thing with this. This n minus 1, it's now unbiased, which is beautiful. How much time do we have? Not enough to talk about the standard error. Do you have a question?
What makes it unbiased?
Okay, that's actually a really good question. So with n, we've said that it's probably going to underestimate, right? So if we make the denominator smaller, that will make this ratio larger, right? So 2 divided by 2 is 1. But if I make the denominator smaller, right? So 1, you can imagine that is underestimating the true variance. But if I get rid of that 2 in the denominator and replace it with 1, now that's equal to 2. 2 divided by 1, which is a larger estimate. So on average, this will provide you with larger estimates than just the n will. And will overcome, not necessarily, because we could easily say something like we're going to do n minus 1.
Oh, okay.
And then that would provide you, actually even n minus 2 would give you a biased estimate again. But then in that situation, it would be an overestimate. And the reasoning for why n minus 1 works is way beyond the scope of this class, but if you're interested, come to my office and we can talk.
That's scary.
See you guys.